Okay, so last time we spent a lot of time talking about this quantum PCP conjecture, which is an analog of the quantum PCP theorem. So let me just write down what the conjecture is. At least, we saw two formulations, and we spent a lot of time talking about this Hamiltonian formulation, which I'll write here. So the conjecture is that there exists some constant k and numbers alpha and beta that are distinct, that are between 0 and 1, such that the following decision problem is QMA complete. Oh, Andrew, you volunteered for describing. We already have the volunteers, but maybe next week. Thanks. So such that the following decision problem is QMA complete, right? So as usual, you're given a K local Hamiltonian as input. Okay. And you have to determine whether it's a yes instance or a no instance, where the yes instances are the ground energy of this local Hamiltonian is at most this constant alpha times the number of terms. Okay, and in the no instance, you have that the ground energy is above beta times m, right? So this is the conjecture. And just recall that what we do know is true is this quantum Cook-Levin theorem, which, the problem that is QMA complete is the same problem, except that the difference between the yes and no instances is just some inverse polynomial amount. So something that's like a vanishingly small number. But the quantum PCP conjecture is stating that, in fact, it's still QMA hard when the difference between the yes and no instances is very large. Something that's growing as a function of the number of terms or the number of particles involved in the system. So we don't know this is true, and I sort of went into this informal discussion of what would the implications be if this PCP conjecture were true. Namely, it would have implications possibly for many-body physics. Right, and we had some pretty good discussion about that last time, and we'll continue it a little longer for today. So intuitively, if this quantum PCP conjecture were true, and we also made some very natural complexity theory assumptions. So let's see, quantum PCP plus some complexity assumptions. It would imply the existence of local Hamiltonians whose, and I'll use some scare quotes here, room temperature states would exhibit high complexity. In particular, the entanglement in these states would be not classically describable. So what I want to do right now is actually just make this statement and this formulation a little more precise, so we know what we're talking about. So the first thing I want to do is I want to define what I mean by high complexity, right? So So I have to introduce some sort of measure of complexity of quantum states. Okay, so let's say you're given an n qubit state. Then I'm going to define its complexity to be the minimum depth of a circuit that's required to create this state. This is the where if you took this circuit and you applied it to, say, some initial state, like the all zero state, you would actually get the desired target state. All right. So let's get a feel for, this measure.
Henry, is this in the basis where psi is the easiest to prepare? Because I can prepare the plus state as complexity 1 and like applying Adamar on every qubit. But if I just move to the X basis, then I don't need to do anything and I'm already in the plus state.
Mm-hmm. So here, I guess we're just assuming for simplicity that we're starting in the all zero state. So to create the plus state, like you mentioned, you would have to apply a layer of Hadamard's. So the depth would be 1. So I guess it's just sort of, it's in the same way that for a quantum circuit, you have to fix some particular gate set and you just stick with it. For this definition, you pick some initial starting state. And in this case, we'll pick the all zero state. You could also define it to be the all plus state, for example, and it wouldn't really fundamentally change how you use this measure.
But I mean more that the complexity of a quantum state depends on the basis you chose to describe your problem in. So, for example, you could map your problem to a quantum computer working in the diagonal basis of the Hamiltonian already. Then all the eigenstates would just be basis states, basically. But if you work in some other basis, then these eigenstates are highly entangled. So, so when you say that the complexity of psi, is it in the basis where it's the easiest to prepare, or I mean, does it change anything?
I see. Well, I guess whenever you're talking about a quantum state, you're going to fix some, like when you're talking about n qubit states, right? So you have some particular representation for the basis of each qubit. And then if you have a state psi, then on n qubits, then of course there's always a basis in which your state psi looks like the all zero state. But that's, I mean, somehow that doesn't, that would be too easy, right? So I guess the point is,
maybe just the complexity depends on the basis you look at.
Yeah, it definitely depends on the basis. I guess the point is, you fix a basis for each of the qubits, and you just leave that fixed, and then all your states you talk about are with respect to that basis.
Okay, great, thanks.
I guess one can also phrase this definition in algebraic terms, like the minimal amount of unitary operations you need to apply on the 1, 0, 0, 0, 0, 0, 0 vector to get the vector that represents your state. Or am I not getting this right?
Yes, that's exactly right. So here in circuit, yeah, actually I should have said in the circuit, we only allow say 2 qubit gates.
Oh.
Right. Otherwise, if your circuit could be an arbitrary unitary, then in some sense, every state can be prepared in depth 1 because you would just have a unitary that maps to that state. So maybe this is related to what Alexandre was asking. But here we're only allowing 2 qubit gates. let's say it's an arbitrary 2-qubit gate. You can pick any one, but they have to be 2 qubits. And the question is, given those, what's the minimum number of layers do you need to prepare the target state psi? So let's just look at a couple examples to get a feel for this measure. Any product state, so let's say your state psi is just a tensor product of individual qubits, right? So each of these psi i's are going to be just 1 qubit states. Then what's the circuit complexity of this, of such a state? Right. At least, asymptotically, this will be. Okay.
The max of the complexity of each of them?
Good. And the complexity of each state will be, it'll be, as Abhinav says, order 1. It's a constant, right? Because basically you just have a gate prepare each state, but you do it all in parallel, right? So you have the all zeros, and we also allow 1 qubit gates too. Okay. We just have, each of these unitaries will be the one that maps, the state 0 to the state psi 1, psi I. Right. So you only need 1 layer, so this is order 1. Okay, so product states have trivial circuit complexity. So whenever it has order 1, we just say this is trivial. Okay, so we're kind of saying that product states or unentangled states are not that interesting. What's a more interesting state? Well, let's look at what's called the cat state, okay, also known as the GHZ state. So this is just the equal superposition between all zeros and all ones. Okay. Does anyone have an idea about what's the complexity of this state? What depth circuit do you need to create this? Okay, Abhinav says n+1. That is an upper bound, but you can do better.
I have an intuition that says log n, but I'm really not sure. It's like, I don't know.
So log n is indeed the right answer. You can build the state in log n depth. That's very good. Basically, you just kind of, well, actually, maybe I'll leave it as an exercise for you to work out on your own. Actually, this is something that you'll see on your problem set. So, okay. Okay, so this is slightly more interesting. This cat state has some entanglement, right? And this circuit complexity kind of captures it. And the final example that we'll see is something that's on the way other extreme of the spectrum, which is if you take a random quantum state. So there is a well-defined notion in which you can sample an n-qubit quantum state uniformly at random. And this thing is going to be a super complicated mess. It's going to have maximal circuit complexity with very high probability. So a random quantum state with high probability satisfies its complexity being, it's actually going to be exponentially large in n, right? And this is the maximum amount, right? You can approximately prepare, or actually, as you can build an arbitrarily good approximation of any quantum state you want with exponential size circuits.
What's the omega for?
The omega is to just hide some constants yeah, I mean, you know, there's some constant in front of the n. It's not going to be like e to the n exactly, but there's going to be some constant there.
I mean, once we're here, what's the difference between like omega and big O notation?
Oh, good question. So basically, big O means like at most, and then omega means at least, up to some constant. So, right, so like, you know, f is equal to O of g if f is less than c times g, roughly speaking. Whereas if f is omega of g, then this basically means there is some constant, and we're not necessarily keeping track, but there is some universal constant for which f is greater than c times g. So f and g are functions here that you know, go off into infinity.
Henry, I have a quick question.
Yeah.
I'm kind of surprised by this exponential thing, because my memory of this might be mistaken, but I thought that you can create an arbitrary unitary on n qubits in order n squared qubits. Just the combination of all single qubit rotations and all 2-qubit controlled rotations.
So here we're talking about so you're talking about the number of qubits required, but we're talking about circuit circuit size. So definitely circuits like, I mean, if you just sort of like roughly count the number of unitaries, I mean, there's an infinite number of them, but like if you sort of discretize, then the number of unitaries is going to be doubly exponential in n. So basically that means like in general, the number of gates you would need to produce a generic unitary would be exponential in n.
Does this bound assume a gate set like Clifford plus T gate set, or if you had like a continuous gate set there, that would be a different bound?
It doesn't matter. So here I'm allowing arbitrary 2-qubit, 1 and 2-qubit gates, so it can be continuous. If you restrict to Clifford and T, it'd be the same thing. The difference is just you can only implement unitaries approximately rather than exactly. Whereas if you allow arbitrary 2-qubit gates, then you can actually, with sufficiently many gates, implement every unitary exactly. But qualitatively, these bounds will all be the same. Okay, so
Henry, can you say something more about how you sample a random quantum state?
How do you sample one? Well, I guess the technical definition is that there's, you know, the set of all quantum states on n qubits is you can think of it as like the unit sphere in dimensions 2 to the n. And so this is you know, it's a compact set, and you can define something called the Haar measure. I forget what's the notation. I know it's like projective space on C2 to the n, or, you know, something like that. You know, there's like a rotationally invariant measure on this, which you can sample from. If you're saying like, what is a mathematical procedure to actually sample from it? One way to do it is you can just pick a vector of length 2 to the n, and each entry you independently pick a random Gaussian, and then you just divide by the norm of this vector, and then you'll get a uniformly random unit vector.
I see, thanks.
Okay, so this complexity measure, it's like has high dynamic range, right? Like it can be anywhere from like 0 all the way to exponential and n. And so there's this huge range, right, for possibilities for the complexity of a quantum state. And we can think of the complexity of a measure as capturing how complicated is the entanglement inherent in the state. And the complexity is measured by, you get to someone hands you the state and you get to try to pick what is the shortest possible circuit I can try to build in order to get this state. And if the shortest circuit still requires exponential depth or super polynomial depth, then it tells you that, it's really, complicated. And we can think that the states that at least we can get our hands on in this universe efficiently will be the ones that have polynomial complexity. So morally speaking, the physically relevant states, the ones that you could hope to observe in a lab or something, are going to be the ones that have polynomial complexity. Right? Because if it has more than polynomial complexity, you have no hope in general of ever seeing it in front of you.
Why is that, Henry?
Oh, so yeah, I mean, also, I'm often, the last couple lectures, I'm making a lot of these moral statements, but feel free to fight back. So basically, we're equating polynomial time as what's efficiently doable in a reasonable amount of time. And, asymptotically, we can think of, things that take exponential time. So let's say you have a 300 qubit state. Something that's exponential in 300 is 2 to the 300. There haven't been that many nanoseconds or Planck times in the history of the universe, right? So if something requires a circuit of depth 2 to the 300 in order to prepare, we can be pretty sure that there is no physical process in this universe that could have produced it, right? So we don't expect to see such states around.
Well, there is no
Though if
deterministic process that produced it. But maybe there is randomness in the world. Like, I don't know.
In the natural world, do you have that everything goes like evolves by 2 qubit unitaries, or could you possibly have that like you get this state because these n qubits all just do the unitary that you want?
Yeah, these are great questions. So let's see. Let me answer Yuval's. So sorry, Yuval's question was what was your question again?
Like, I don't know if this question even makes sense, but like the world may be random in some sense, and thus if
right. So maybe there's some random process out, in some galaxy somewhere that, just spits out these states of exponential complexity. That's possible, but then, if you try to imagine, well, what is this random process? It's some, I mean, ultimately we think if you assume that, that the laws of nature obey quantum mechanics and obey maybe the standard model of physics, then whatever random process, it's just really occurring because of local forces that are interacting in some ways, and some particles are bumping into each other, and things are being measured and so on. But all of this, we believe, can be simulated by a quantum computer, right? This is just a belief, right? This is called the quantum Turing thesis, that any physical process that exists in the universe, you can simulate efficiently using a quantum computer. So, whatever crazy thing is going on in the next galaxy over, we're going to assume that it could have been simulated by polynomial time quantum computers. So therefore, all the states that this galaxy could have produced should have polynomial complexity. Right, and maybe that And that also maybe answers Hugh's question. Oh, you were asking about the 2-qubit gates, right? So we think that, yeah, and when I say quantum computer, I mean one that operates using 2-qubit gates.
I feel like this could blow up with recursion, though. Like, the wave function of the universe, say, includes perhaps in some portion of it the wave function of a quantum computer that is solving a problem that is QMA complete. Right? That's a physically possible process. And so this would seem to imply that it's polynomially hard to simulate the solving of a QMA complete problem, which looks to me like QMA equals BQP.
Right. So so we have to be careful what we mean by, what does it mean for something to solve a QMA complete problem? And here, this is where it's important to remember, are we solving a specific instance? Because we can always get lucky. For example, like if you want to solve an NP complete problem or a QMA complete problem, you can just run you know, your favorite algorithm to try to solve it, and you know, maybe you'll make the correct guesses and you'll find the correct solution. But in general, we don't expect such an algorithm to succeed on all possible instances. So let me say it again. Solving a QMA complete problem, it means that you can solve it in polynomial time no matter what instance you give to it. And that's not something that you can necessarily so, okay, well, I don't know if that answered your question. So if you're saying, like, you know, this wave function of, if you're simulating the universe and inside this universe, there's a computer that happens to solve an instance of a QMA complete problem, there's no contradiction there, because it doesn't mean that we've found a polynomial time algorithm to solve all instances of, say, the local Hamiltonian problem.
Oh yeah, right, because like any instance could have some tailor-made algorithm.
Yes.
Solving it. And that drops the complexity down considerably.
Right. So you know, in that sense, when we talk about solving problems, we really mean that can you solve all instances, or like a large, you know, an infinite number of possible instances, and that's when it makes sense to say whether you're solving it in polynomial time or not. Actually, you know, I should, you know, maybe this is familiar to a lot of people, but, you know, when I use the terms polynomial or exponential, this only makes sense when you're talking about a growing number of you know, there's some asymptotic quantity. Like, for example, it doesn't make sense to say, is the number 100 polynomial or exponential, right? That's like meaningless. It's only what you're saying as a function of something that you imagine as going off to infinity, like the number of particles or something like that.
One more pushback on this physically relevant states equals polynomial complexity piece. Relates to what someone was asking before about this kind of being basis dependent. So I agree that for our analysis of like a quantum computer, a quantum algorithm or something, we fix, you know, the gates that are allowed, we fix the basis we're working in. But it might be kind of like the universe is working in some other basis and produces some state in polynomial time in that basis, but that's kind of one that in our basis would require an exponentially large circuit to create.
Okay, yeah, that's a good point you raise. So here, it's true that if you're allowed arbitrary changes of basis, then you can, something that would have been easy in one basis could be difficult in another, and vice versa. But actually, we sort of think that we only should allow basis changes that are local. Like you should really only be able to change the basis of you know, individual qubits separately, but you shouldn't be able to like completely change the basis in which you're like you know, the entire basis of your laboratory, or you know, change the entire basis of 300 qubits all at the same time.
So I hear the point you're trying to make, but that's kind of like, that's our choice. When we decide to analyze a quantum system, it's our choice of how to factor the larger Hilbert space
Yes.
into smaller ones.
Right. That's right. So, so I guess then, the question I have for you is there is there like some experiment that you can run where, you have a bunch of different particles that you sort of factored out. It's like, okay, there's a particle here, 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 but then I can do a large change of basis that simultaneously sort of smears out all these different, qubits together into something that's completely different. And as far as I can tell, I don't think we know of physical processes that look like that.
Fair enough, although I don't know of any reason why there couldn't be.
Yeah, if there is, then okay, so the point is, if there is something like that, then you might hope to possibly take advantage of that to gain some sort of speed up. But I think what the this Church-Turing thesis that I mentioned sort of posits or assumes that such a thing is not really possible. But if you can always prove it wrong by saying, hey, look, I found a physical process that does allow me to make this change of basis.
So wait, sorry, just back to what you were saying before. So you're saying that we believe that any like physical quantum system that if it runs quote unquote quickly, then we can simulate it in like quote unquote polynomial time with like 2-qubit gates. Like efficient physical quantum processes can be like efficiently simulated by these 2-qubit gates.
Yeah, well, I don't want to speak for all of us, but that is the content. Yeah, that is the content of this quantum Church-Turing thesis. But there actually is you can try to back it up by saying, what's the most general theory of nature that we have? Well, I think a lot of people say the standard model of quantum field theory or quantum physics, and people have shown, at least, there are papers showing that it's very plausible that you can simulate all of, there are algorithms for simulating the standard model on a quantum computer. It's not like fully proven, but I think they have pretty compelling arguments for saying that here is an algorithm that can simulate, how all the fields interact and, whatever
in an efficient way.
In an efficient way, all in polynomial time. So, yeah, maybe I'll send a link in the chat to this paper. There's a couple papers that show how to do this. So if you think the universe is governed by the standard model, then we believe you can simulate it in quantum polynomial time.
Hey, Henry. Yeah, just a question. So, yeah, coming back to complexity theory. So we have, in the classical case, we have, like a 5n circuit lower bound, right? That's the best we have. So what are some popular, famous analogous cases for quantum circuits, or I don't know, of these proof states? And what would they say about QMA not equal to BQP? So,
that's a great question. So the basic answer is we have, if you think we know very little in the classical complexity theory, we know even less in quantum complexity theory. It's, just to say some things like, for example, we don't even know the analog of parity not in, it's an open question of whether parity can be solved in quantum AC0. This is actually something that like Greg has worked on.
Yeah.
So we don't know that. There's this thing with quantum state complexity, which I find very interesting, because in some sense, there's no analog so the analog of this quantum state complexity is this thing known as Komogorov complexity, which you might have heard of. Mm-hmm. The Komogorov complexity, it's a much limited range. it's a measure of how complex or how random a string is, and it's either between 0 and n. Whereas here it's between 0 and exponential and n. So there's like a much bigger range for things to happen. One really interesting question I have is basically the best lower bound that we can explicitly prove on any family of states is this one, is a log n lower bound.
Really?
And it's a very, I mean, you can probably prove it yourself, but one open question I think would be really interesting is, can you find a family of states for which there's a super logarithmic lower bound?
Hmm.
And as far as I can tell, there's no barriers to proving this. Like usually, you know, there's lots of complexity barriers for things, but yeah, I mean, there's no barriers that I know of. Show family of states such that the complexity of this is much bigger than log n, say like log squared n.
And do people have candidates for this?
No, I don't think many people have thought about this.
Oh,
yeah.
It's like intuitively, why is the case? Because like it's difficult to describe complex states. So like to describe these increasingly complex states would be, I guess, difficult to do.
Yeah, you always run into problems like when you want to show something requires a large circuit to produce, you have to say there is no possible way of coming up with any simpler circuit. But our understanding of what's possible, what you can do with simple circuits is we have a very, we don't have a very good handle on that. So, basically there's just like a lack of understanding, a lack of techniques. But also it makes it like very exciting because to me, this is such a basic question.
So again, just a question: how do you prove that this is like the best possible scenario? Like, let's say, like, because again, we cannot produce all these states, right? For like, let's say, 1 billion qubits or something like that.
Mm-hmm.
And you don't know if there is a, like, I don't know, easier circuit or something like that. So how can we, like, yeah, I can do maybe like when you're thinking about proving these things, I can like iteratively build up circuits and the best circuits for, let's say, 2, 3, 4 qubits. There might be some tricks here, but who knows what happens when you like jump or bump up the number of qubits in the state, right? So how can you like say that this is the best you can do?
That's a very good question. It's something that, the basic answer is we have very, very few techniques for doing so. Like, let me just give a sketch of how do you argue this. So I said the exercise is to prove that you can do it in log n, but let me argue that you need at least log n depth to do it. And it's kind of what's called a light cone argument. What color should I use today? So let me draw it here. So basically you say, well, imagine for contradiction that there was a circuit. Let's even do some, like, kind of for simplicity, let's imagine that there was like a depth 10 circuit that prepared the cat state, right? That started from, all zeros and somehow produced this cat state. Well, the observation is that you look at, this output qubit here, in some sense only can notice, or it only depends on all the qubits in its past light cone, in the sense that if you sort of propagate, and I'm being very wishy-washy here, but you can actually make this formal, like the dependence of this qubit, it can only notice the state of the input qubits that are connected to it. So there's at most 2 to the d input qubits that could possibly affect this output qubit. So that's not hard to show, but then and what you deduce is that if you can find a far away another output qubit that's far away that has its own light cone that's disjoint. So it would say that these two output qubits are behaving independently, but in this cat state, that's definitely not the case. Like if you know that this first qubit is 0, like if you measure this first output qubit and you get outcome 0, then you know that this output qubit also has to be 0.
Yeah.
Right. So
okay.
So that's sort of how you argue that you can't have a circuit that's too short depth. And embarrassingly, this is essentially the only technique that we have for proving quantum circuit lower bounds. Okay. And you can sort of see why we run into this log barrier, because once d is log n, then this is equal to n.
Yeah. Okay. Thanks.
Okay. Yeah. Great questions. So we have this complexity measure, and let's come back to local Hamiltonians. There's this measure motivates the following question: which local Hamiltonians have ground states, or low energy states for some definition of low, with polynomial complexity. Okay, so this is a question you can ask, and a potential answer that would be really interesting if this were true would be, say, all physically relevant local Hamiltonians. Physically relevant in the sense that it's the type of local Hamiltonian that you would encounter out in nature. If this were true, then this would mean that you can always describe, these physically relevant systems with polynomial size classical descriptions. They're classical descriptions because you can just describe the circuit that produces the state. We don't know that this is true, and it would be, interesting either way. So we don't know. But we can sort of think, well, what if, maybe we can define a complexity class that captures these types of local Hamiltonians. So there's this complexity class that's a variant of QMA called QCMA. So this stands for quantum classical. And I personally think this is a horrible complexity class name, but people have just stuck with it. So QCMA. And it's actually horrible for a number of reasons. One is that it completely misrepresents what it means. But the idea is that it's just like QMA, but Merlin can only send a classical proof. So Arthur is quantum polynomial time. And then Merlin is, he's all wise and all powerful, but he can only send a classical string that Arthur verifies. Okay.
So in particular, he can only send a quantum state, which is polynomial complexity.
Yes. Right. So this is sort of a more restricted version of QMA. And in terms of what decision problems it contains, well, it's going to be a subset of QMA. We don't know if they're the same or not. But I mean, the question of whether they're the same is really like it sort of captures this question right here. Like if they were the same, then it would say that essentially you can always describe ground states, you can always give like a classical proof of a ground state. You know, a classical proof that a local Hamiltonian has a low energy state. And then a reasonable conjecture, well, reasonable to some people, is that they're different. That actually, the ability for Merlin to send you a quantum state to convince you of something is actually a powerful ability. Okay, so this would imply that not all local Hamiltonians have polynomial complexity ground states. Okay. So let's connect this to the quantum PCP conjecture. So QPCP plus the assumption that QCMA is different from QMA would imply that not only do ground states in general don't have polynomial complexity, but even if you consider states that have much higher energies, right, up to this medium energy range. So it would imply that there are local Hamiltonians whose states with energy less than beta m, where this beta m is this, you know, threshold between yes and no, right? This that any states that have energy less than this cannot have polynomial complexity. Or I should say, all have super polynomial complexity. Okay. And so this is sort of you know, getting closer to, or this is a more precise way of stating what this many body physics implication of the quantum PCP conjecture would be. And you know, what does this have to do with temperature, right? I was saying like room temperature, right? And again, you know, there's this loose connection between energy and temperature. We can actually make this a little more precise, and I kind of alluded to this last time. So what's the connection to room temperature? So, you know, remember that a local Hamiltonian describes a physical system, like what are the forces at play, the interactions, the constraint of some physical system. So here's a local Hamiltonian. Here's a system S with a bunch of particles, right? You know, some qubits. So this Hamiltonian describes the interactions, right? And depending on the configuration of your particles, you know, your system would have different energies. Let's imagine that, and okay, I'm going to start to get into territory that I'm kind of a novice in, but you know, people who know better help me out. So when you have the system and you put it into contact with an external environment, right? So I'm going to put it in contact with something known as a bath that's, you know, much bigger than this system S, right? And this bath has, you know, you can think of it as having an infinite number of particles, and it's like in equilibrium, and it's, you know, there's some interactions between these two. And, you know, this bath is at some temperature T. And if you sort of let these two systems interact and equilibrate, eventually both systems will be in temperature T. And then you can ask, well, what is the state of this system S? And it'll be in something known as a Gibbs state. So it represents the state of the system at thermal equilibrium. And what is this Gibbs state? Well, I'm going to denote it. It's a function of the Hamiltonian and the temperature. And it's the following density matrix. It's going to be 1 over Z. And it's going to be e to the minus h over t. And what is Z? It's the normalization constant. It's the trace of this operator. Okay, so you can verify for yourself that this is a density matrix. Okay, it represents a probabilistic mixture of pure states. It's a density matrix on n qubits. Okay. And it's supposed to represent like the sort of the distribution of states of the system S. Okay, so what are some features of this Gibbs state? So, here's where we can connect things to like what I said, the minimum eigenvalue is like absolute 0, and we can make that formal. So as you drive the temperature down to 0, then this Gibbs state approaches the uniform distribution over the ground space of your Hamiltonian, right? So it's really just going to be just an equal mixture of ground states, right? So it's really kind of tells you that if the temperature of this bath was, going to absolute 0, then really that's going to cool your system down to the ground state. On the other hand, if you're going to crank up the temperature to make things hotter and hotter, then your Gibbs state is actually going to approach what's called the maximally mixed state. So it's 2 to the minus n times the identity. So this is a density matrix. This is the maximally mixed state, right? And let me emphasize, it's the maximally mixed state as opposed to the maximally entangled state. In fact, this state has no entanglement whatsoever, right? It's completely featureless. I mean, this state just looks like the uniform distribution over all classical bit strings, right? So if we took a Hamiltonian that had a complicated ground state at ground 0, but then you cranked up the temperature, it's going to lose all of its quantum effects as things go to as the temperature goes to infinity. So given like a Hamiltonian, you can ask, well, what's the crossover point between when the Gibbs state has high complexity and to when it has low complexity, right? There's a certain temperature at which there's some transition point. Right, so actually let me, so here the complexity of this mixed state, and what I mean by this is that, it's a mixture of what's like the average complexity of all the states in its mixture. It's going to be, very large, say super polynomial. But here the complexity of this maximally mixed state is going to be 0. Or order 1. So it went from very large to order 1, and at what point does it switch over? Okay, and so what the quantum PCP conjecture says, quantum PCP plus QMA not equals to QCMA, it implies there exists local Hamiltonians where the complexity of this Gibbs state remains high even when the temperature is some growing function of the number of particles. Okay. And so this is really how you can make this claim that it's saying something about room temperature entanglement. You can make this statement precise. And actually, in the next problem set, you'll make all of these statements more precise and quantitative.
So, like, you're assuming that there's some threshold phenomena here.
I guess there's not necessarily a threshold phenomenon. I guess I want to say, what's the point at which it switches from we're also talking, asymptotically, right? But is
okay.
there a point at which it switches from super polynomial to polynomial?
Okay.
Yeah.
Henry, is it known that, I guess, if QPCP and QCMA is not equal to QMA, then the same local Hamiltonian H works for both implications? Or could they possibly be different?
You mean for QPCP and QCMA not equal to QMA?
Right. So I guess you have two different implications, but I guess are they known to imply each other?
Oh, you mean what I wrote before, like this one,
right?
And the Gibbs state one? Oh, right. They're roughly equivalent, and actually, the equivalence is what you'll prove in the problem set.
I guess that kind of makes sense.
Yeah. Okay, so let's take a 5-minute break. So let's come back at 5:11-ish. But we can continue chatting if people have more questions.
So Henry, I just found a paper that I was trying to recall. I can post it in the chat.
Okay.
So I'm not quite familiar with the work, but I know I knew that David Poulin very well, and yeah, it seems to say that that most states in the Hilbert space are not physical because they looked at which states could be prepared with a time evolution under a local Hamiltonian or time-dependent local Hamiltonian in polynomial time, and they found out that this set of states occupies only an exponentially small fraction of the total Hilbert space. So I think that's an important result there, which kind of corroborates what you were saying.
Mm-hmm. I just need to get past the paywall. Okay,
so yeah, I can also share the PDF on Slack, I guess.
Oh, sure. Yeah. Yeah, I think this is basically in the same spirit of what I was saying. But I would imagine that they didn't actually identify, they didn't pin down any specific states that would require an exponential amount of time to produce. So that if you just sort of close your eyes and just reached out and grabbed a quantum state at random with high probability, it's going to be exponentially complex. But to actually guarantee to me that a state has exponential complexity, this is something we don't know how to do.
Right.
Yeah.
Uh-huh. Yeah, and also you can think of someone before quantum computers, you ask them, okay, is it possible to store a 300 qubit state? Then they say, no, that's impossible. I mean, we don't have the technology to do that or whatever. But then today is possible. So, but it's hard to prove that there is no technology that we don't know that can prepare in polynomial amount of time state.
Right.
My power went out for a few minutes at physically relevant states.
Oh no.
So did I miss anything important?
Well, the good thing is that this video is recorded. So
cool.
That was quite some time ago, right? Like that was like half an hour ago or something?
I think like 10 minutes ago or something.
Okay, I think we were just mostly chatting. But yeah, everything will be recorded, so
okay, cool.
You can review.
Oh yeah, I don't think last week's recording is out yet.
Is it not? I thought I posted it.
Yeah.
Did I post it?
I think it was posted in the Slack.
Oh, okay.
Like a week ago, almost.
Let's see. Yeah, it's a video of lecture 5. So, so if you have access to the Slack, you should be able to see it.
All right, thanks.
Can you please repeat the last sentence that you wrote there? There exists local Hamiltonians where the complexity, even when t scales with number of particles. I feel like there's a word missing there somewhere, or I'm not understanding it.
Is there? Oh, where the complexity? Yeah, complexity is super polynomial.
Oh, okay.
Yeah. Yeah, great.
Yeah, I wanted to ask, so what restrictions of quantum circuits have been studied? So, I mean, again, comparing it to the classical case, of course, you study bounded depth quantum circuits, but apart from that, I mean, you study monotone classical circuits, you study, let's say, formulas, right? So have people looked into proving lower bounds for maybe restricted settings of quantum circuits?
Very little. I think we just don't have enough interesting classes of restricted classes of circuits that are amenable for analysis. But I don't know, people think about, yeah, right, constant depth. I think people think a lot about circuits where the connectivity between the qubits are all arranged in like a grid or in some, you know, there's some like limited connectivity. I mean, because that's motivated by actually trying to build these computers. In terms of other restrictions,
how would you define a monotone quantum circuit? Like, what does it mean?
That's a good question. I don't know. I mean,
what about the formula, though? What
formula? So formulas. So remind me, formulas are where you cannot repeat input bits, right?
Yeah.
So
so the underlying tree is acyclic, yeah.
Right. So I guess with quantum circuits, you're not allowed to copy quantum bits anyways. So yeah, that's a good question. I don't know. Yeah.
Or I guess equivalently, formulas are just log depth circuits.
Yeah. So so the notion of there's this model of quantum AC0, which is supposed to be the quantum analog of classical AC0, and there it's like the standard model where you have 2 qubit gates, but they also throw in these really long range gates called quantum fan out, which allows you to copy input bits. Sorry, okay, let me back up. There's 2 notions of quantum AC0, one with or without fan out. And this is sort of like the big question, are they the same? With fan out, where you're allowed to copy input bits, it's actually a really powerful resource. You can solve parity in constant depth. using this fan-out gate, which is very curious. And so the question is, well, if you don't have this fan-out gate, but you have these other types of long-range gates, can you still solve parity? It's not known.
Sorry, what do you mean by long-range gate?
Oh, gates that act on like a growing number of qubits all at once, like, you know, like a square root n size gate or something. Okay, so
but I guess in the AC0 model, your fan-in is unlimited anyway.
Yes.
Right.
Right, yeah. Mm-hmm.
I guess it's interesting because I think you mentioned, Henry, that like people in like experimentalists are implementing these like fan-out gates or something like that.
Yeah, so there was a paper that came out a month or two ago that said on like ion traps that you can actually do quantum fan-out, which might mean you can solve parity in constant depth circuits, quantum circuits, which would be pretty cool. Okay, so let's get back to it. Let's see, pull out my notes. Okay, so I want to talk about some no-go results. And basically this is, you know, I've stated this quantum PCP conjecture. A lot of people find it very interesting. So what's known about it? Not a lot. Basically, the best things we know is if you were to try to prove quantum PCP, here's what you shouldn't do. That's basically what people know. So I'll cover them. One is quantum PCP cannot hold for local Hamiltonians defined on a grid. So, okay, so what do I mean by this? Well, quantum PCP is saying that, you know, we're restricted to local Hamiltonians where you can encode QMA hard problems into them. And it's QMA hard even to tell whether they have like really, really high ground energy or really, really low ground energy. So ultimately, if you were to say prove the quantum PCP theorem, you're going to construct a really exotic family of local Hamiltonians. Just like, you know, when we constructed this Cook-Levin theorem, this Feynman-Kitaev Hamiltonian had, you know, it has some qualities, right? Like it's, you know, it has like these, you know, these clock qubits, and it has these like starts okay, evolves okay, ends okay terms, and so on, right? So you've constructed some family of Hamiltonians. Quantum PCP requires some other construction, but what we know is that your local Hamiltonians cannot have constraints that lie on a grid. So what I mean by this is that you can't have a Hamiltonian where you have qubits in, say, some 2D grid. Say qubits are all in the corners here, and then all the Hamiltonian terms act on nearest neighbors. And why is that the case? Well, the point is, if you had a local Hamiltonian of this form, so let's say it's if qubit I is connected to qubit J, then you have a term connecting them. If you had a Hamiltonian of this form, then in fact you can always approximate the ground state using a product state, right? So actually there's just very, very little entanglement needed to describe a low energy state. And that would mean that you know, you can always give like a classical description, but if you're assuming this thing that, you know, QMA hard problems can't have efficient classical descriptions, then this would be a contradiction. Okay. So basically what I'm going to show is that you can approximate So the way we're going to do this is, so let's say our grid was n qubits by n qubits. So there's n squared qubits total. And we're going to chop up the grid into little L by L patches. So or L by L blocks, right? So we can say, let's block together these L qubits. Right, and then, we just put the blocks together like this. So let me just tile them. And so ultimately we're going to get n squared divided by L squared blocks, right? And within a block, we can, there's a bunch of Hamiltonian terms, and we can group the Hamiltonian terms together. So let's see, how should I, let's label each block, 1 through n squared over L squared. And I'm going to define a new Hamiltonian term for the ith block. So this is going to be the sum over all, say, qubits. Qubit k is connected to qubit L, and both are, k and L are in the ith block. Right, so you're going to look in a block and you're just going to look which Hamiltonian terms go between qubits that are within the block, and we're just going to include those. Okay, so I'm going to call this hi prime a super term. Right, it's a super Hamiltonian term. You just sort of cluster them together. And I'll define a new Hamiltonian that I call, well, actually, let me say, the original Hamiltonian H can be written as a sum of these super terms. Right? So let me call this M, right? There's M blocks, right? But we've omitted some terms, right? Namely the terms that go in between the blocks. So I'll just call those the boundary terms, and I'll just bundle them all together into another super term called H boundary. Okay. Does that make sense, what I'm doing? Okay, let's first just do a quick count of how many boundary terms there are. So each block has, roughly 4L boundary terms, right? And there's n squared over L squared blocks. So in total, there are 4n squared over L boundary terms.
Divided by 2, maybe?
Divided by 2? Oh, yeah, probably, because you're double counting or something, right? Yeah, so let's say at most 4n squared over L boundary terms. All right, okay, so let's look at a super term H prime I, right? It's by itself, this is like a mini local Hamiltonian that acts on L squared qubits. Okay, and let's think of L as just being some large enough constant like 100. Okay, so it's just some constant. It's not growing with the size of your grid. And the ground state of this mini Hamiltonian can be found in 2 to the L squared time. you just brute force this little patch and solve for the ground state. Right, so let's call a ground state psi sub I. Okay. So for each of these blocks, we're going to individually solve for those ground states, and then we'll just piece them together. And so we'll just say, I'm going to define a state that's going to be my approximation of the global ground state as the tensor product of, patch 1 up to patch n squared over L squared of psi I. Right? So this whole state is going to be on n squared qubits, right? It's on n by n qubits. But since it's this product state, it's going to have a very succinct description. Right? I can describe it just using, just by describing each of the psi i's individually, right? So it's, it can be described in, the number of patches times the size of each, the description size of each ground state individually. And, this is still, if L is a constant, then this is still polynomial at n. Right? And now let's compute its energy, and let's show that it actually has a pretty low energy.
Just one quick thing. When you say brute force on HI prime, you mean like take the matrix and compute its and compute its en vector corresponding to its smallest en value. Okay.
Yeah. That, or that's one possible way to do it. Okay, so let's expand out what this is. Let's first sum over all the patches. So we're going to have psi inner product patch I, and then we have these boundary terms. Right. So here since this is identity on all but L squared qubits, we can actually just, and this psi is a tensor product of states, we can just isolate the ith ground state. So this is just equal to summation over I, psi I, hi prime, psi I, and then we still have this boundary component, right? Here, I'm just going to upper bound this just by the norm of this Hamiltonian, all these boundary terms. And, basically we can just upper bound this by counting the number of terms that are present. And how many terms are there? Well, that's the number of boundary terms. We've calculated this to be 4n squared over L. Some constant, of n squared over L. Right. Everyone following so far? So now we just have to see how well, we want to relate this to the minimum eigenvalue of H, right? So let's do another calculation, which is let's take the actual ground state of H. So let's let theta be actual ground state of H. So we know that lambda min of H is going to be the energy of theta. And this is going to be at least, again, we're going to sum over these super terms. We have theta, hi prime, theta, and we actually can just drop the boundary term because that's always, the energy of theta with respect to the boundary terms is always non-negative, so we can just ignore it. But now I claim that each of these, we're trying to here minimize, okay, the energy of theta with respect to this super term hi is always going to be at least the thing that we already found to minimize it. Okay. So basically we can now just combine these two derivations, and what do we get? We get that the energy of these block states is going to be at most the minimum eigenvalue of h plus this error term, which is 4n squared over L. So we're only doing worse than the minimum energy by this this additive factor 4n squared over L. Let me normalize this to be more in line with how we've been talking about the quantum PCP theorem. Like we're talking about the, beta m or alpha m, where m is the number of terms. So, the number of terms is going to be, order n squared. So if we do the substitution, we see that really this error term is the number of terms divided by this L, which is some large constant. Okay, so suppose that, okay, how does this tie into sorry. So let's say that
your screen stopped sharing.
Oh, it is stopped sharing. Oh, let's see. What do you see now? I'll start broadcast. Okay, are we back?
Yep.
Okay, awesome. Yep. Thanks. Okay, so coming back to so why is this a no-go result for quantum PCP? Well, the point is that here's a state for H that only has, m over L extra energy above the ground energy, and it has a very succinct classical description. And if, m over L is much, much smaller than the difference between beta minus alpha m, then, then we're technically in the yes case, right? Because, it means that the minimum, the ground energy of this local Hamiltonian is going to be much smaller than beta times m. So which means H is in the yes case, but has a low complexity, low energy state. Okay, so does that make sense to people? Okay, and there's nothing special about 2D grids in this argument. This could have applied to any finite dimensional grid. So the argument, right? And it says that basically these types of local Hamiltonians, even though they're very commonly considered in many body physics, things interacting on grids, they're too simple to be the types of Hamiltonians that the quantum PCP conjecture would be like most interested in.
So just to get it straight, so we basically solve this problem in polynomial time, deterministically, in the case that we have a grid. Because in the yes case, we can find a certificate that says that we are far from the no case in polynomial time.
Mm-hmm.
Oh, okay, thank you.
Right. So these grid Hamiltonians are too simple for quantum PCP.
But Henry, can because there are again algorithms which use things like that, and they consider some of these boundary terms or like the crosstalk, and but then they are able to get like, at least for a few there has been a few papers which actually propose this kind of splitting the whole system into smaller blocks and then trying to correlate them later. And they are able to get like pretty good approximations to the ground state energy. So like, what does that tell you here? That that is a good way of solving like the ground state energy of any k-local Hamiltonian, right?
If the interactions are neatly arranged in this grid-like structure.
So like basically you don't need a quantum computer if that, but anyways, you can like break down these interactions into just local, but anyways, you only have local interactions, right? When you're going to run this on a quantum computer or something like that, because when you want to correlate two things that are far apart from that, you break them into like just nearest neighbor interactions, and like you might end up paying extra depth or extra gate depth or something like that, but that still works, right?
Well, as whether something or not, I guess it depends on how accurate you want your answers to be.
Yeah, so exactly. So can we say something about how good your actual ground state energy would be if you use something like this based on classical approximation or classical methods or something like that?
Let's see. So I guess I'm not sure on this distinction being so here I'm talking just about a classical method to solve this.
Yeah.
And the result is okay. So it's a solution, but what is the quality of the solution? It gives you an additive error of m divided by L, and in many cases this is like too big of an error.
Okay.
Right. So oftentimes you want to do much better than this for if you actually want to solve this in practice.
So like, yeah, okay, so like exactly, like so like, because there is literally an exact quantum algorithm which does this, which basically breaks the grid into small blocks, and then once you have solved these small blocks, it transforms the Hamiltonian, or like to take into consideration these crosstalk between these two blocks. And like, so basically that algorithm almost gives you the same effect as the classical algorithm or something like that, or is there even a need for like a quantum algorithm for this case, like problem like this?
I see what you're saying. So I'm not so familiar with the quantum algorithms for this. Well, I can say this though. In general, you won't be, even with a quantum algorithm, you won't be able to solve these 2D grid systems exactly. Like you won't be able to find approximations to the ground energy that are, say, inverse polynomial close to the true answer. And that's because these grid Hamiltonians are still complicated enough that you can put QMA complete problems on them.
Okay.
So really here the distinguishing thing is what quality of approximation you're willing to tolerate. If you want a very good approximation, then even a quantum algorithm won't help you in polynomial time. But we're saying if you're willing to tolerate a very coarse approximation, something as big as m over L, then there's a polynomial time algorithm to do it for you.
Okay, so basically, if you're like, it depends on the threshold of error that you're willing to accommodate.
Yes. Yeah.
Okay. Yeah, thanks.
Yeah, very good question. Okay, so let me move on to the, there's one more no-go result to kind of illustrate something that's different. So this, basically, yeah, it holds this argument. You can also run it for, 3D grids or 4D grids or what have you, or more generally, any graph that can be decomposed into small pieces, right? Like you can imagine a Hamiltonian whose interactions are defined on an arbitrary graph. So here's some graph, right? So the qubits sit on the vertices and then the edges connect the different vertices. But if your graph is decomposable, where you can chop it up into small pieces, and then there's very few terms crossing the pieces, then you could, the same argument holds, right? This isn't, so from a complexity theory point of view, this is not so surprising, because actually the same argument holds for the classical PCP theorem as well. Right? It's saying that, okay, so we know the classical PCP theorem is true, it's proved, and the result, it produces these, the theorem produces these very interesting constraint satisfaction problems, like these 3-set instances, where, it's hard to tell whether, half of the clauses are satisfiable or almost all of the clauses are satisfiable. And these 3-set instances that are produced by the theorem are not going to be on this grid for exactly the same reasons. And in fact, these 3-set instances will have a much more complicated system of interactions. Right, so you look at all the clauses and the constraints in these CSPs and how they connect to the different variables, and it forms a graph. And these graphs are going to be very highly connected, right? They're going to form what's called an expander graph. Expander graphs are those that it's basically impossible to decompose it into small pieces without cutting a lot of edges. Okay, so knowing this is what the classical PCP theorem produces, you might be inspired to say, well, maybe we can engineer local Hamiltonians where all the interactions lie on an expander graph, and maybe that's the way to go. This is a very natural thing. But what's funny is that if you go too far, it actually starts backfiring, right? So, so classically, the better expanding your interaction graph gets, meaning the more highly connected it is, the better PCP theorem you can prove. So what I mean that, like, as you increase the expansion properties of your graph, then the resulting classical PCP theorem that you get has better and better parameters. It's like a stronger statement. But quantumly, this is not the case. So this is a very, very like, initially this was like a very counterintuitive result, saying that actually if you had like a system of like a local Hamiltonian whose interactions are sitting on an extremely good expander, it's actually also not going to be that complicated. Like you can also find ground states that have pretty short descriptions. So here's a, and this was shown in a theorem by Brandau and Harrow. And they said, you know, suppose you had a two local Hamiltonian. So the, okay, so you basically have interactions between two qubits each. Then there exists a product state okay, where each psi I is a state on some small cluster of n over t qubits. Where the energy of this product state is actually going to be pretty good. It's going to be the minimum energy plus something related to how good of an expander your graph is. Where, okay, what are these numbers? So m is, again, the number of terms of your Hamiltonian. And this phi sub g is going to be, it's going to be a measure of the expansion of your graph, the interaction graph G. Okay, and this is a number between 1/2 and 0. Okay, so this is a theorem that they proved, and as you get a better and better expander, so this is as you get close to 1/2, this is going to be better expansion. Then this error term is going to get closer and closer to 0, which means you get a better and better approximation of the ground state. Okay, but on the other hand, if you have terrible expansion, like if you know, you make this expansion go to 0, then that means you can chop it up into, you know, your interaction graph into small pieces, and then you can use the same, you know, the argument that I presented before to get also a good product state approximation of the ground state. Okay, so you know, it's kind of like a weird lose-lose situation.
Sorry, Henry. Does the like intuition behind this proof come from the fact that when you have, let's say, a lot of these terms are talking to each other, like the influence that each of them have on each of them is not as great. So like you have a better expansion or you have better approximation, but when you have like very few terms that talk like between these blocks or between these two like graphs or something, you cannot neglect them. So like if you neglect them, your approximation is bad. Something.
Let's see. So this statement is sort of saying that you, at least in the 1/2 or 0 regime, you get good approximations. It doesn't say anything about having bad approximations.
So basically what I meant was like, let's say like, because when you're saying better expansion, like when 5G approaches half, it basically means you cannot construct blocks, right? Which are without cutting terms, without like neglecting some of these Hamiltonian terms that act between these two subgraphs, right?
Right.
So does like, my question was, does the, like, if I had to think about why this is the case, that when this is the case, when you cannot cut and there are a lot of terms,
right.
Does the physical motive, or like if I had to think in the physical terms, like, because there are a lot of terms that are like doing these crosstalks between these subgraphs, right? That's why the 5G, or like, that's why it's hard to like separate them. So to have an approximation that is good, you can basically neglect some of these terms because they might come into effect because of some other terms that are already being considered in some other graphs. But when the case, or when you cannot separate the full graph into smaller graphs, and like there are only a few terms that are there. Like so, like you now have to cut, or you now have to neglect very small number of Hamiltonian terms between or these subgraphs. Then these have higher effects on the approximations that you make.
Mm-hmm. So, I mean, it sounds reasonable, but one thing to notice is that the intuition you're providing somehow isn't taking into account whether your system is classical or quantum. Mm-hmm. So we know that if you have a classical constraint satisfaction problem, or in other words, like a classical Hamiltonian, then as the expansion gets closer and closer to half, it's actually harder and harder to find good approximations to the lowest mm-hmm. energy state. Okay. So really what's happening here is kind of like a genuinely quantum phenomenon. When you have like more and more connectivity between your interactions, it actually forces, basically the upshot is forcing your ground states to become more and more classical.
Okay. So because like in chemistry, like when we talk about these correlated systems, so like when you have these electrons that are like, there are a lot of these correlated systems where you have, let's say, a lot of, or there are terms which are very important if you neglect them. Like imagine all these electrons sitting on a grid, and there are these highly correlated systems where if you neglect one of these terms, so like if you wanted to do an approximation where you wanted to consider a product state where you did not consider crosstalk, that would lead to very bad approximations, because it's like literally the opposite case. Like if you don't consider the full Hamiltonian terms, your approximations would be very bad. Mm-hmm. And on the opposite side, when they are not highly correlated systems, then sure. If you consider product state, it works pretty good. Mm-hmm. Like that. So like, right. Like this is kind of the opposite, like for correlated systems in chemistry. Just
I see. Right. I mean, this is in some sense, this is maybe a little more surprising. But this is really saying, like, if you pack in a lot of cross terms, mm-hmm. and I think like sort of maybe way more than what you might encounter in quantum chemistry or something, then it says that you can, to use some physics terminology, that these mean field approximations are actually quite good. Mean field means like product state approximations, right? Mm-hmm. And that's what's really behind this theorem, is that once your interactions just get really, really dense and highly connected, your ground states don't need any entanglement. So the intuition comes from this thing that we discussed earlier, which is this monogamy of entanglement. Which says that, if you have a bunch of particles, but they all have constraints on all of them. And, you can think of each of these constraints as saying, oh, we all want you to be maximally entangled with each other. But that's not possible. The only way to sort of, there's no entangled state that, satisfies all of these constraints, and really they're just forced to be product states. Yeah.
So how about graphs that have very bad expansion, but you cannot decompose into small pieces? For example, take a click, take another click, connect them by an edge.
Right. So then you can sort of like interleave both arguments. You just divide, you chop the two clicks in half, and then you know that this clique and this clique are super good expanders, and then you just sort of find the product state approximations for both, and then
yeah, sure, but like now let's say you have square root of n cliques, and you connect each one by an edge.
Yeah, I think you know, here, okay, so the point here is that we're actually willing to tolerate a lot of errors, like a constant fraction of the number of edges. So, you know, you should keep that in mind. So if you have a lot of cliques, but then you connect them with single edges, you know, the number of inter-clique connections is relatively small compared to the total number of edges in this entire graph.
It's about the same asymptotically, because you have square root of n cliques, you connect one edge between each pair of cliques.
Yep.
And each clique contains also a linear in n amount of edges.
Right.
So it's n inside and n outside, but maybe that's still.
Okay, so yeah, but you're basically homing in like, can we find examples of graphs for which maybe we can noodle our way around this? That's possible. So, you know, I guess the punchline is that we've at least identified the extreme ends of which we know it's not possible, and we're really looking for some Goldilocks solution where, you know, it's expanding but not too expanding. The main lesson that this theorem of Brandau-Harrow is telling us, and there's like a related theorem that says actually also your graph cannot have too high a degree, like a particle cannot talk to too many other particles.
Mm-hmm.
Exactly for this monogamy of entanglement reason. But of course, like you said, it's easy to come up with graphs that sort of avoid all of these, but then all of these constraints.
You can replace each one of my cliques of say square root of n with a constant degree expander, and so like you would have like graphs with degree 4 or 5, but still they are not that well connected.
Right. So it's possible, and this is not covered by the theorem of Brandau-Harrow. But you know, there's still some sense that this would be too easy of a solution. It is say, oh, let's just make the cliques a little smaller and so on.
Okay, sure.
Yeah, but we, you know, we don't know. So this is basically what we know about quantum PCP. You know, it's which is to say not much, but I think it's really intriguing. Like, basically, can we imagine and come up with really exotic types of local Hamiltonians that have really exotic low energy states that exhibit all sorts of weird entanglement? And basically the best candidates for such weird Hamiltonians are ones that come from quantum error correcting codes. Quantum error correcting codes give rise to Hamiltonians, and we sort of by definition, the quantum error correcting codes have to like create states with really, really robust forms of entanglement, right? So by definition, so it seems like a good place to start, and really that's what people are looking into. But yeah, you know, the story's still open. Okay, so basically we've reached the end of the part of a class on Hamiltonian complexity. Yeah, so hopefully you know, you got a sense of the lay of the land. I was gonna, you know, if I had half an hour left, I was going to start a section on QMA2, but I might, you know, move this to next time. But maybe not. So the next, you know, unit of this class will switch gears. We're not going to talk much about Hamiltonians anymore, although they'll actually make an appearance in certain places. But we're going to talk about something called the verification of quantum systems and the things related to that. So yeah, that's it for today.
is it possible that like the set of all local Hamiltonians that can be represented by a graph, so I guess two local Hamiltonians aren't complex enough for this quantum PCP conjecture?
Yeah, I didn't mention this, but you say, well, why do the interactions have to only involve 2 qubits? Why can't they involve 3? And we also don't know very much. We don't have any barrier results there. Yeah, I mean, especially like all these like error correcting codes, the interactions involve like a small cluster of qubits. Right. Definitely not 2. So, you can also say that this theorem, this Brandau-Harrow, is really ruling out a very, very narrow class of graphs or local Hamiltonians. That's right. Definitely, I think that's probably definitely clear.
I guess something that a lot of people are excited about nowadays is this theory of like high dimensional expansion, like expansion not just on a graph, but I guess some high dimensional simplicial complex. Like, have people looked into that in relation to quantum PCPs, or is it wide open?
It's wide open. I have a very, very strong feeling that that's pretty intimately connected to what's needed to move forward on this quantum PCP. Like these highly structured, like these high dimensional expanders are kind of like on the border between like being very structured but not too structured objects. And that's sort of, the feeling is that you need something like that straddles the borderline to really construct these local Hamiltonians. But I guess we're also seeing that high dimensional expanders are useful for other things not related to quantum. So I think it's, yeah, really interesting.
Is there an analog of sort of a Goldwasser-Sebser theorem for QMA2, like round reduction? Like in terms of public coins versus private coins.
Oh, QMA2, yeah, so I didn't get into this, but QMA2 here refers to the model of QMA where Merlin sends you 2 proofs that are promised to be unentangled.
Oh, so it's not a one of interaction.
It's not about interaction.
Oh, okay.
Yeah.
Okay.
But the question you asked is also very interesting. I think what you're talking about is there's these classes called QAM or QIP with 2 rounds, and these classes are very poorly understood. Like they sort of, no one's pinned down exactly what their complexity is. Wow.
Okay.
Actually, I think I will cover QMA2 because it's just so cool. Just to give a preview, so I said, Merlin can send you these 2 unentangled proofs. And this is actually a very powerful promise, as far as we can tell, because in general, if someone hands you a quantum state on 2 registers, there's no measurement that you can do to detect whether these 2 registers are entangled with each other or not. So having the guarantee that the 2 registers are unentangled, you can actually use that to your advantage. And so one of the things you can do with this is there's a QMA2 protocol for 3-sat. Someone can convince you that a 3-sat formula on n variables is satisfiable, but they only need to send you a square root n sized proof. But if you don't have this unentanglement guarantee, then even if Merlin can hand you a quantum state, we still think that to convince you of 3 satisfiability, they still need to send you n qubits. So with unentanglement, you can somehow compress your proof size in certain cases. So okay, I think I'll talk about this next time.
Henry, just like, yeah, is there a good review kind of thing on like the work up till now in quantum complexity theory? A good review which you will recommend reading or something like that?
So for Hamiltonian, yeah, I can. In the Slack, I posted one about quantum PCP, so that just talks about this subject. There's a good review on quantum Hamiltonian complexity that I can link. And that covers a lot of cool topics. There's a lot of other things in quantum complexity theory that people think about. I don't think there's an all-encompassing survey of those other topics.
Yeah, like it would be cool just to read a bit about the Hamiltonian complexity. Like,
sure.
Yeah.
Yeah, I'll post a link.
Thank you.
Yeah. Okay, so just a reminder, I'll keep your eye out for the problem set in the next couple of days and start trying to form project groups. All right, so have a great week, everyone.
You too, thanks.
Thanks, you too.